Hello and welcome to another tutorial. In this tutorial I'm going to continue our discussion on numerically finding roots of a real function, and we are looking for the real roots. And if you recall, we started with looking at the general lemma. So if we said that if we have a continuous function f of x and we want to find the real roots of f of x equals 0. Now continuity, we're assuming that the function is continuous over the interval that we are searching for the roots. Now it could be discontinuous over other intervals, which we don't care. But if we are looking for the roots over some interval a and b, here we're assuming that the function is continuous over this interval. And if it's continuous and the value of the function changes sign between the initial point and the end point of the interval, this lemma guarantees that there is at least one root in this interval, right? The exact number of roots is not guaranteed, that's for sure, but if the continuity is satisfied, then we definitely have at least one root over this interval. There is no way for a continuous function to change sign from A to B but not crossing the horizontal axis. So it has to cross the horizontal axis in order to change sign from A to B. And we said that this lemma is the fundamental or the basis for the most fundamental root finding algorithm, which is the bisection method, and its order is log. By order I mean the number of steps, because it's at the end of the day all the root finding algorithms are iterations or generate a sequence of real numbers that hopefully converge to the exact value of the root, right? So it's basically iterations. At each iteration the algorithm pushes the estimation closer and closer to the root, or at least that's what we hope for. And there are some tests to see whether or not this iteration or the sequence of the approximations are actually converging or not. All right, and we said that the bisection is a very fundamental method, and it's the simplest method, which means from the function f of x, the only information that you need to calculate is just the values of the function at some points, right? And the basic idea was that break the interval in halves, and in each half apply the general lemma. Okay, if we know that we have a root, then one of these paths should converge the root. If we do not have roots, the algorithm should return a nan, not a number, right? And we said that in Java we use the double dot nan from the double, and it's better to return nan instead of returning a null value. Okay, and the only problem with bisection is when the function is actually tangent. So we have a tangent root, and we said that this means that the behavior of the function is some even. If you use the Taylor expansion of the function around this root, the behavior is x minus root squared, or the power of 4 to power of 6, or any even power of x minus r. That's how the function behaves. That's basically the format of the Taylor series around this root. Okay, and and we also talked about the error, and we said that if you look at the sequence of the approximations for the root, and we define the relative error of the convergence or the absolute error, then the relative error depends on the size of the initial interval b minus a, and because at each step we're dividing the interval by half, the worst case error also is reduced by half, because the worst case of error, at some point we have to call it the convergence, which means at some point we end up with a small interval, and the worst case, and we have to pick a point in that interval and call it the approximation of the root. And we said that the best thing to do is just pick the mid value of that interval. So the worst case eventually becomes the length of the final interval, and the worst case error is also reduced by a factor of 2 each time. So the number of steps that we actually need to get the error that we want is like 2. And then we said that we can make it we can go one step further, and instead of starting with the midpoint, because there are cases that the root might be closer to one edge of the initial interval, right? And we might have an idea of the approximation of the root. So we can also include an initial guess for the root. So we put the initial guess and then we do the bisection on those two intervals instead of the midpoint, okay? So that's one way that we can make a little bit of improvement. And in Java, we said that almost all these root finding algorithms are kind of recursive. So we use recursion, which is a very powerful tool for implementing these root finding algorithms. We defined the function, the real function, we defined it as an interface, so it automatically enforces the function to be real. And then it's a functional interface, so we can easily use lambda expressions. And then we created a class for finding roots, and we implemented the bisection method. The initial interval, we did not implement initial guess yet, but we will do it later. And we did the binary search using recursion. And we also set up the stop criteria based on the absolute error and the relative error. Now, the idea is that, okay, let's say bisection can give us at least one root, but what if we are interested in finding all the roots? Now, the very simple thing to do is, if we are interested in finding all the roots over the interval a and b, let's just initially break the interval into smaller subintervals. Let's say 100 subintervals, all right? So, I mean, we are most likely going to hit all the roots if we run the bisection on all these subintervals, okay? So, the advantage here is that bisection was very simple, and it required the least amount of calculations, right? Because we only have to calculate the value of the function. We don't care about the derivative, the second derivative, or whatever, which some other root finding algorithms actually need to calculate the derivatives, which adds more cost of computation. But because bisection is pretty much fast and requires minimum calculations compared to other methods, then we can run it over a lot of subintervals, right? The only problem is that, okay, the bisection doesn't actually work for the tangent roots when the function is tangent, but for now let's disregard that case. We can patch it with some other methods, or we can patch the bisection with other conditions, or use other root finding algorithms in conjunction with the bisection. But for now, let's assume that none of the roots are tangent roots. So what we're going to do is that in the step 1, we're going to break the initial interval into smaller subintervals, 10, 20, 100. Doesn't add more overhead because bisection in general is pretty fast. And then we run the bisection over all these intervals, and if you recall, if the bisection converges to the root, it returns a double value, the root. If it doesn't converge, if you recall, we implemented the nan, so it results in nan, or it returns a nan, which is, here it's an advantage of returning nan. Then we can check whether or not, if the bisection returns nan, means there is no root in this interval, okay? We might run into duplicate roots. We can also check for that. So the best thing to do is that to create a list, data structure. If you're not familiar with the collections framework in Java, I suggest you look into that. So we are using collection framework, okay? So we're using collection framework in Java to keep track of the roots and test for the NaN, also test for the duplicates. So you can use an array list. So you can either use an array list or use a set interface. So I'm going to use an array list, but we can also use a array list of doubles, or you can use a set value of the set. Set automatically checks for duplicates, so it might be easier to use a set, but I'm going to use a list just for simplicity. All right, let's head to Eclipse and try to implement this. So we had this demo roots projects, and we already implemented the functional interface for a real root function, and we pass this interface to the real root. So it automatically enforces the fact that the function should be real. All right, so it returns a double value. And then in the real root, we have the real root function, and we pass it to the constructor of the real root, and it sets the function. And we already implemented the bisection method, the stop conditions for the convergence, and then if it returns NaN, we know that the bisection failed, we didn't find any roots. Otherwise, it goes either into the first half of the interval or the second half. All right, now let's create our new method. So let's say finding all the roots based on the bisection method. And public, and so instead of returning a double value, we want to return all roots. So we're going to return a list of double values and bisection, double start, double end, and we're going to add an integer parameter, and we call it sub intervals. So this is basically the user can determine how many sub intervals he or she wants. So let's import the list from the Java util package. Make sure that you import the right list object. It's from Java utils. So we're going to create a list of double. We'll call it roots. So this is plural roots, which means it contains all the roots. New array list of double. All right, and we need to import the array list too. I'm going to import it from Java util. All right, we actually don't need to put the double here. The constructor, the compiler can confer actually what's the type of this generic implementation, which is here. All right, okay, so eventually we're going to return roots. So initially all the stuff in the roots are null values, all the numbers. So what are we going to do? We're going to divide it into the number of sub intervals. So what we need here is, let's create an array, call it points. These are the endpoints of the intervals. Points, new double array of sub intervals plus 1. So if I want 2 sub interval, I have to have 3 points on the interval, the beginning, the mid, and the end. All right, and then we write a for loop, int I equals 0, I less than points dot length I plus plus, and we need to also define the length of each interval, which is the end minus start divided by sub intervals. All right, I call it dx. You can call it whatever you want. So if because the length, the number of points is sub plus 1, so then points I is start point plus I times dx, and this is going to be inclusive of start and end points, because obviously if I is 0, we already have the start at the beginning, but for the end point, when I is the sub interval, We have start plus subinterval times dx, which is end minus start divided by subintervals. So we end up with end. So it's inclusive of the start and end points. All right. Now we have all the points. Let's run the bisection. Run the bisection on each subinterval. So we're writing a for again. For int I equals 0, I less than points dot length, or let's just go subinterval I plus plus. We're going to write some ifs. So what we want to do eventually is to have the create a double value, call it, let's say, potential root, and call the bisection method points I and points I plus 1. All right. Obviously we don't want to run into array out of bound exception, so I should go from 0 to length of points minus 1. All right, minus 2. So the last index should be length of points minus 1, which is subinterval. So I should go from 0 to subintervals minus 1. Then we have subintervals minus 1 and the subinterval. Okay, that's why here I put subintervals, which is length of points minus 1. And then what we're going to do, we're going to add this potential root to our list of roots if it passes our checks. So we have to add the checks. One is double is nan, which is potential root. So if it's not nan, so I'm going to negate it. We're going to add the roots dot add potential root. But that's not the only test. I'm going to also test for duplicates. So test for nan and duplicates. Basically what I'm going to do, I'm going to add a logical and say that not roots already contains potential root. So if it's not nan, is nan, which is negated, and roots already contains this potential root and negated. So if it doesn't already contain the potential root and it's not nan, add it to the list of roots, and then we're going to return the roots. All right. Okay, so now let's go to our test bisection method, and let's create another static method here, public static void test2. I'm going to run test2, and let's do exactly what we did. So define function, I'm using lambda expression, x times x minus 2. And then we're going to have real root, call it roots, plural, and let's just call it func, new real root, and we're going to pass the func. And then we're going to, or let's call it root finder, that's a more appropriate name, root finder. And then we're going to create a list of doubles, roots, root finder, bisection. But this time, instead of returning a double, I'm going to invoke the other one that returns a list. A start, which is let's say -5 to 10 or 3, and let's go with 100 subintervals, and just we're going to return the roots. We're going to print line roots, and the list. Okay, we need to import the list. Make sure you import it from the Java util. And the list already overrides the toString method, so no need to worry about toString for list objects. It already puts them in a nice way. All right, test2, we should have 2 roots. Let's see. Oh, let's go also remove all these print lines. here, stopped, half, first half, second half. Let's remove that from the bisection and let's run it again. Bingo. So we have two roots, minus a square root of 2 and plus a square root of 2, and it's pretty fast. Let's call it 1. So minus 1 1 1, bingo. Now what happens if it's tangent? So x squared is tangent and the root is 0. Yeah, it still can't find it, which is very interesting. It doesn't guarantee that it can find the oh, actually that's because I'm thinking that that's because it's maybe it's because the original objects, the roots are 0, so that could be one possibility. Let's write it as x minus 2 times x minus 2. If this returns 0, it means that it actually fails to find the root. No, it can actually find the root, which is very interesting. I wasn't expecting that. Now, for example, let's say we say math.sine of x, all right? And then let's go from 0 to 4 pi. Let's see how many roots we find. 0, pi, 2 pi, 3 pi, and 4 pi. So this is a very strong method for finding all the roots. Now if we have, let's see what happens if we have sine x squared. Now this function, sine of x squared, has basically a lot of oscillations, and that would cause a lot of roots. So it's interesting. So I'm going to, from 0 to pi, we have 0, 1, 2, 3, 3 roots, and let's plot the function sine of x squared and actually verify and then verify the roots. So plotting is one way to verify the roots. And how do we plot that? If you recall, I said that in the mathlib library there is a package plot, and there is one object, MATLAB chart, which utilizes the JFree library, JFree chart. We will return to JFree chart and review it, but for now you can just use this MATLAB chart, which is a wrapper class. So MATLAB chart, fig new MATLAB chart. So we create an empty chart, and then I'm going to go to the build path and give it a dependency on the mathlib, and then we're going to import this, and then I'm going to create the array of doubles x mathutils dot line space from 0 to math.pi, let's say 10,000 steps, and then we're going to run the function over this over all these values. So if you recall, I mentioned you can use the array func, apply, and it takes the interface of real function, but it's different from this. So we're going to use the lambda expression value t, and then over the array of x. All right, so that's one of the beauties about using a functional interface. If you have another function, you can just use the lambda expression to explicitly define the interface. And then we're going to plot x and y, and then fig dot, we're going to render it to create the panel, and then fig dot run, and we're going to exit the application. All right. And what I need to do, I need to go to the run configuration because I'm using Mac, and remove this check mark. All right, this is the function. So we have a 0 at 0, which is correct, and then we have another 0 here, which is let me just increase the font size. It's about 1.77 something, and which is correct. And then we have another 0 here, at around 2.5, 2.5066, and another 0 here, 3.07, 3.0699. So as you can see, our root finding algorithm based on the bisection method is very powerful and can in fact succeed in returning all the roots. Now we see if I increase the order of the function or use different functions, let's call this test 3. Let's say sine x times x again, so cube. Let's see what happens. Yeah, we have how many roots do we have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 roots. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So our algorithm seems to succeed. At 0, the first root is around 1.5, 1.4659. The next one is around 1.84, and all the way to the last root, which is around 3.04, 3.046. All right. So this was our discussion on the finding all the real roots of a real function over a given interval. The condition is that the function is supposed to be continuous over that interval, and we're using the underlying very fast bisection method, which only returns one root or returns none. It fails. And then we basically, what we do, we just divide the interval into very small subintervals and run the bisection over that, and disregard the roots that are basically none, or roots that are repeating themselves. And this proves to be a very strong way of finding all the roots. Thank you for watching, and I'll see you in the next video.